In this video, I'm going to do a DC analysis of a transistor. So here we have a NPN transistor. How do we know NPN transistor? Based on this arrow. This arrow is going to be always on the emitter. If this arrow is going out, then definitely that is an NPN transistor. If the arrow is going in, then that's a PNP transistor. Okay, so that's how I know NPN and PNP transistor. So here our goal is finding the voltages at each node, the base and emitter and collector, as well as we want to find the currents flowing through each branch or each of those nodes. To make it simple, first thing I'm going to do, here I have two resistors and two voltage sources. I'm going to convert them and combine them, make it as a single source and single resistor. How are we going to do it? So I'm going to cut the wire right there. So I'm going to separate it. So when we redraw this circuit diagram, it's going to be look like this. So now I'm going to find the Thevenin equivalent circuit. So when I find the Thevenin equivalent circuit, the voltage here, I'm going to call it as a VBB. I applied the KCL at this node. So by using that KCL, I found VBB equal to 10 volts. After solving this, we end up finding VBB equal to 10 volts. Now we need to find the equivalent resistance of those two. So while finding the resistance, what we do, we'll replace all the independent voltage sources with their internal resistance, which is short circuit. If it is a current source, it's with the open circuit. So here we have 100K, 100K. Now I'm finding the equivalent resistance here, RBB. So you can clearly see 100K parallel with 100K. So I'm going to call the equivalent resistance is 50K ohm. Now I'm going to attach this. So what I have, VBB, which is 10 volt, and RBB, which is 50K. I'm going to connect this circuit back right here in this circuit. So I'm going to redraw the circuit here again. So here is the equivalent circuit after converting the base resistance and base voltage into a single voltage source and single resistor. So this is my VB. This is NPN transistor. How do I know? Based on this arrow, that's an emitter and this collector. Now, few important things we need to know. The current passing through this emitter, I'm calling that as IE. Current here is IC and current here is IB. Okay. For NPN transistor, IB is going in, IC is also going in, IE is coming out. So here always, no matter what, IE must be equal to IB plus IC. Always this is true, no matter what, whether this is NPN transistor or PNP transistor. And I'm going to solve PNP transistor later on in another video. Here for any transistor, beta value is always given. So in this example, the beta value is given as 100. Beta is common emitter current gain. So beta is common emitter current gain. That value is always given. Now the relation between the beta gives you relation between IC and IB. Beta is always equal to IC over IB, and alpha equal to IC over IE. So here beta is common emitter current gain, alpha is common base current gain. Alpha value is always less than 1, close to 1 most probably, and beta value is in between 50 to 200. That value is always given by the manufacturer. So here in this example, he gave us the beta value as 100. Here he gave us the beta value as 100. Now we're going to start solving the example by assuming this transistor is in active mode of operation. So when it is in active mode, always base to emitter junction is always forward biased. So in active mode of operation, this junction, base to emitter junction, is always forward biased, and this collector to base junction is reverse biased. So in active mode of operation, this transistor is going to act like an amplifier, so to amplify the signal. So there are three modes of operation mainly. One is cutoff mode, where in cutoff mode these two junctions are going to act like a reverse biased, so it's going to act like an open switch. In active mode, this base to emitter is always forward biased and base to collector is reverse biased, so it is in active mode. In saturation mode, both junctions are going to be forward biased. Saturation mode is nothing but it's going to act like a closer switch. So in saturation mode, the beta value does not work. I mean, it doesn't have any value. We'll have a new beta value which is going to be beta forced. Now another important point I want to discuss before I forget, IE equal to IB plus IC. This IB is the current passing through the base, which is very small compared to IC and IE. So IB is very small compared to IC. So since IB is very small, you can say IE is approximately IC, approximately equal to IC, but we do not take that. IE is always equal to IC. We always use this equation. It's just like the current, the voltage at VB always controls the current passing through this emitter and the collector. That's what the transistor does. Okay. To avoid confusion, I redraw the circuit here. So now I'm taking this as an active mode of operation. So we'll take this as 0.7 volt, since this junction is forward biased, base to emitter junction is forward biased. Now I'm going to apply KVL here. So if I apply KVL there, it's going to be minus 10 plus 50 IB plus 0.7 plus 2K times IE equal to 0. This is one of the equation. Now I already know IB, I can write it as IB, I can write it as IC over beta. IB equal to IC over beta, and same thing IE equal to IC over alpha. IE equal to IC over alpha. So based on this, I can find the IC. So what I'm going to do, I'm going to substitute these two equations, IB and IE values, right here. I mean, this is IE and this is IB. So that's what I'm going to do. So it's going to be, small correction, I forgot, I mentioned it's 50K, actually 50 ohms, but actual value is 50K ohms. So I just corrected it here. So that's 50K ohms. So it's 50K here. So here I solved the equation. I found IC equal to 3.69 milliampere. Once I have IC, I can find IE as well as IB. Since I know beta value, I know IB equal to IC over beta, so which is 3.69 milli divided by 100. That will give us like 36.9 microampere. So as I mentioned, IB is very small compared to IC and IE, and here is my IB. Now based on this, I can find IE equal to IB plus IC, or you can use the alpha value and find IE. So I found IE equal to 3.727 milliampere. Once I know IE, now remember we started solving this example by assuming it is in active mode of operation. So we need to verify whether it is in active mode of operation or not. To verify, all we need to do is make sure this VCE is greater than 0.3 volts. As long as VCE is greater than 0.3 volts, that transistor is in active mode. So to find VCE, all I need to do is find VC and find VE. We are good to go. What is VC? VC must be 15 minus 2 kilo times IC, which is 3.69 milliampere, and VE equal to IE times RE, So 3.727k, sorry, milli times 2k. That will give me VE value. So we can find VCE. So here I have VC equal to 8.22 volts, VE equal to 7.45 volts. So VCE is 8.22 minus 7.45, definitely, which is greater than 0.3 volt. So this transistor is working in active mode of operation. So that's all we need to find. Okay, in the next example I'm going to solve another NPN transistor DC analysis, and then following video most probably I'm going to do a PNP transistor. Thank you guys.